This is the fifth lab and final lab presentation of the semester, and it deals with Faraday's law. So the introduction and purpose of this lab was to make observations and motion predictions of a magnet falling through a conducting tube. For this scenario, an aluminum foil, possibly using kinematic equations either from Physics 2011 or high school physics. Additionally, we were to create a computer model that predicts the motion of said falling magnet and compare its findings to our own observational findings. And in the inset of some photos here, you can see 3 kinematic equations that could be very useful in this experiment. So the fundamental principles that we will be using in this project are, of course, Faraday's law, which we use to find the induced currents in each, quote, ring of the tube. A changing magnetic field can induce a current, as we all know. Secondly, we have Newton's second law of motion, which we can use to find the position and velocity of the magnet at each point in the tube. And finally, we have Newton's third law of motion, which can be used to find the force exerted on the magnet by the tube made of rings. To clarify, the aluminum tube is modeled by a series of rings in glow script. The final fundamental principle we have is the Biot-Savart law we've commonly used throughout this course, but this time it's used to find the magnetic field of each current-carrying ring. And the formula for this bar magnet in this niche scenario is listed on the right, which is m mu naught over 4 pi, or 1 times 10 to the negative 7th, times 3 times the magnetic dipole moment of the bar magnet times r hat again minus the magnetic dipole moment all over R3, or the observation location distance cubed. We use this to find the magnetic field over the shaded area, as we did in the edX videos of week 10. Falling times to the bar magnet. For each trial, the time to fall through the length of the aluminum tube was recorded, and the average amount of time to fall through the tube was actually 1.334 seconds. And the measurements for the tube are listed down below. For example, the length of the tube is 0.301 meters, tube width is 0.11 meters, and inner radius is 0.019 meters. And the magnetic dipole moment from lab 3 is 4.375 ampere per meter squared. However, as we found out later, this is much too high. It actually deferred in the computational model for falling times by more than twice the amount of average time for falling for observations, so I clearly had to lower it by more than half. So each outline here from my notes for the calculations, we see the step-by-step, the flux through each ring, induced current in each ring, and the force on each loop due to the bar magnet. And we can see these formulas from my notes derived from the edX videos and the Shabai textbook. These formulas will be incredibly important, and they can be seen in the code later. Finally, this is where third law of motion comes in. We can find the force of the falling magnet due to each current ring. And we have the south pole on the top and the north pole on the bottom. And the force of the loop on the magnet is facing up towards the magnet, and the force of the loop on the magnet is towards the bottom. And finally, we have important code excerpts. We have the code where you can see the bar magnet creation, calculating flux over time, the induced current in each ring, and the calculating magnetic force. The mathematical and computational translations of each formula are actually very smooth and very simple to see. And moreover, when we predict magnetic motion, we have iterative predictions derived from Physics 1, which you can also apply Newton's second law to predict the velocity and position of the magnet. So in my computational model, we have 2 photos derived from running my actual code, and one is captured when the bar magnet is about to fall through the aluminum foil, and one when the bar magnet is actually falling through the foil, and in this model is accompanied by red and blue current carrying rings. And here we have the velocity versus time plot. The time of magnet travel was mapped out to be 1.48 seconds, and this is with my recalculated magnetic dipole of 2.3 amperes meters per second squared. So at the end of each lab, we interpreted the simulation and asked ourselves a series of questions. The first one of which is the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. How do we know which color corresponds to clockwise or counterclockwise? The answer to that is the magnet is dropped with the north pole facing the tube. The bar magnet's magnetic field is pointing downward. Above the magnet, which is a blue ring, the magnetic field is decreasing, so the current is going to be counterclockwise. And conversely, the magnetic field below the magnet is increasing, so current will be going counterclockwise, and this is represented by the red ring. And when we flip the magnet around, this magnetic field would instead increase above the magnet and decrease below the magnet. Therefore, the current in both areas would be flipped. For my total time in tube, for the real world system and the computational system, it was only off by a hundredth of a second, but the computational model is more likely to be accurate since there is no instance of human error of not dropping the magnet recording is timed perfectly for each trial. And finally, my velocity versus time plot reaches zero acceleration inside the tube, which indicates the magnetic force on the bar and the gravitational force are equal, thus leading to a value of zero net force on the magnet. So finally, we have some questions to think about. The first one of which is, what if the resistivity of the conductor were reduced as close as possible to zero? And how would the dynamics of the falling magnet change? The answer to that question is that the resistance of the rings would change, thus allowing the magnet to fall through the tube at a greater velocity and accelerate. By extension, the amount of current in the conductor would increase as well. And finally, what if the holes were cut into the tube, and how would this affect the ring's current in your model? The answer to that is the ring will also fall faster through the tube in this scenario, and this is because the holes would weaken the induced magnetic field.